On February 13th, 2023, at a depth of 3,500 meters in the Mediterranean Sea, absolute darkness was broken by a sudden flash of blue light. It wasn't bioluminescence, it was Cherenkov radiation, an optical shockwave produced when a charged particle outruns light in water. Neutrinos are invisible messengers from deep space. KM3NeT recorded the signature, a track-like muon signal, with an estimated energy in the hundreds of peta-electron volts. Here's the anomaly IceCube in Antarctica, the world's largest neutrino detector, has watched for 15 years and reported nothing comparable. At this energy, the Earth should absorb most particles before they arrive. Yet something still made it through. Was this a rare statistical fluke, or a hint of new physics from the dark sector? Before we can answer that question, we need to understand the stage where it happened. 3.5 kilometers beneath the surface of the Mediterranean, the pressure is crushing over 350 atmospheres. It is a world of eternal night, untouched by sunlight. But for astrophysicists, this darkness is a resource. The ocean here is not merely a biological habitat. It is a massive natural calorimeter, an instrumented volume built to detect the faintest signals from the cosmos. On that February day, the silence of the abyss was broken. When a high-energy neutrino interacts near the detector, it can produce a muon that races through seawater faster than light can travel in that medium. The result was a shockwave of photons known as Cherenkov radiation. It is the optical equivalent of a sonic boom, a cone of deep blue light that screams through the darkness. For the optical modules of KM3NeT, this wasn't just a flash. It was a track-like topology, a distinct track-like signature etched into the data. The energy reconstruction was staggering, estimated to be in the range of hundreds of peta-electron volts, or PeV. To put that into perspective, this single ghost particle carried kinetic energy millions of times greater than the protons we smashed together at the Large Hadron Collider. It was a localized subatomic cataclysm. But this isn't the first time physics has been confronted with an energy budget that doesn't add up. To understand why this one flash matters, we have to reopen the very first missing energy case in the history of physics. Long before we chased signals in seawater, physics faced a simpler, yet more fundamental question. Where did the energy go? In 1930, the scientific community was grappling with a crisis involving beta decay. According to the known laws of physics, when a neutron decays into a proton and an electron, the energy of the outgoing electron should be constant, a sharp, predictable peak. It is a simple two-body problem, but the data told a different story. The observed energy spectrum was continuous. The electrons were emerging with varying amounts of kinetic energy and almost always less than the total available energy. It was a leaking, closed system. The energy budget didn't balance. The discrepancy was so severe that eminent physicists like Niels Bohr were ready to abandon the law of conservation of energy, suggesting it might only apply statistically, not absolutely. It was a moment of desperation for quantum physics at the time. Enter Wolfgang Pauli. On December 4th, 1930, he penned a famous open letter proposing a desperate remedy. To save the law of conservation, Pauli postulated the existence of a third particle, one that was electrically neutral, had a vanishingly small mass, and was carrying away the missing energy undetected. He initially called it a neutron, but Enrico Fermi would later rename it the neutrino, the little neutral one. Mathematically, it was the perfect alibi. By turning the two-body decay into a three-body interaction, the continuous spectrum made sense. But physically, it was a nightmare. Pauli himself reportedly lamented, "I have done a terrible thing. I have postulated a particle that cannot be detected." He wasn't exaggerating. The calculated cross-section for this particle interacting with matter was approximately 10 to the power of minus 44 square centimeters. To guarantee a single collision, you would need to build a wall of solid lead 1 light-year thick. Pauli's idea saved the law, but it created a new problem. How do you catch something that can pass through a planet as if it were empty space? It took 26 years to turn Pauli's mathematical idea into a physical reality. The challenge wasn't just building a detector, it was finding a source intense enough to overcome the abysmal odds of interaction. By the mid-1950s, Clyde Cowan and Frederick Raines launched Project Poltergeist. Their initial, somewhat cinematic plan was to place a detector near an atomic bomb blast shaft. However, they opted for a more controlled continuous source, a nuclear reactor. At the Savannah River plant in South Carolina, the reactor core produced a flux of roughly 10 to the power of 13 antineutrinos per square centimeter per second. It was a deluge of invisible particles. Raines and Cowan set up a tank containing water and cadmium chloride surrounded by photomultiplier tubes, looking for a specific signature inverse beta decay. The logic was the reverse of the process that created the neutrino. An incoming antineutrino would strike a proton in the water, converting it into a neutron and a positron. This interaction would create a distinct double flash signature, the first flash from the positron annihilating with an electron, followed shortly after by a second flash as the neutron was captured, releasing gamma rays. In 1956, the flashes appeared. They had successfully filtered the signal from the cosmic ray background. They sent a telegram to Polly: "We are happy to inform you that we have definitely detected neutrinos, more precisely antineutrinos." The particle had left a confirmed signature. The existence of the neutrino was confirmed, strengthening the emerging framework of particle physics. But nature creates complexity in layers. Raines and Cowan had proven the particle existed, but the sun was about to reveal that the neutrino we found wasn't the simple particle we thought we understood. Deep within the crust of South Dakota, in the dark, humid tunnels of the Homestake gold mine, chemist Ray Davis Jr. constructed one of the most audacious detectors in scientific history. His goal was to measure the sun directly. To do so, he had to insulate his experiment from the noisy chaos of the surface world. He buried a tank containing 100,000 gallons of perchloroethylene common dry cleaning fluid nearly a mile underground. This rock overburden acted as a filter, blocking the constant rain of cosmic rays, leaving only neutrinos particles that rarely interact to pass through the cognitive bunker he had built. The experiment relied on a specific radiochemical transformation. Davis was hunting for electron neutrinos produced by nuclear fusion in the solar core. When one of these neutrinos struck a chlorine-37 atom in the fluid, it would convert it into a radioactive isotope of argon-37. Periodically, Davis would purge the tank with helium to extract these few argon atoms and count their decays. It was atomic-scale needle hunting. The theoretical baseline for this operation was the standard solar model meticulously calculated by physicist John Bacall. The model predicted exactly how many neutrinos the sun's fusion engine should produce and how many Davis should catch. But as the data accumulated over the 1970s and 80s, a disturbing pattern emerged. Davis was consistently finding only about 1/3 of the predicted number. This discrepancy, known as the solar neutrino problem, created a deep rift in the physics community. It was a standoff between theory and experiment. Skeptics argued that the experiment was flawed, that Davis was losing argon atoms in the extraction process. Others attacked the theory, suggesting our understanding of the sun's core temperature or composition was wrong. For 30 years, the missing 2/3 of the solar neutrinos remained an unsolved scientific problem. The paradox suggested a fundamental gap in our understanding of neutrinos. But as it turned out, the detector wasn't broken and the prediction wasn't wrong. The fault lay in our assumption about the particle's identity. The messenger was changing on the way. The solution to the paradox came from the brilliant, enigmatic mind of Bruno Pontecorvo, working from behind the Iron Curtain. He proposed that neutrinos were not fixed in flavor, but could oscillate between identities. In the standard model, we identified neutrinos by their flavor electron muon and tau. Davis's chemical trap was designed specifically to catch electron neutrinos, but Pontecorvo theorized that these flavors were not fixed states. According to quantum mechanics, a neutrino is created as a superposition of 3 different mass states. Think of them as distinct waves traveling together. As these waves propagate through space, they travel at slightly different speeds because of their differing masses. This causes their phases to shift relative to one another. The result is neutrino oscillation. Imagine a pitcher throwing a baseball. It leaves his hand as a baseball, an electron neutrino, but on the way, it doesn't physically transform into a new object. The quantum mixture shifts, and the same neutrino can arrive with a different detectable flavor, muon or tau. Davis was standing at the plate with a glove made only for baseballs. The tennis balls and golf balls were passing right through his tank, invisible to his chemistry, but fully present in the flux. This theory was definitively confirmed in 2001 by the Sudbury Neutrino Observatory, or SNO, in Canada. Using 1,000 tons of heavy water, SNO was able to detect all three flavors. They found that the total number of neutrinos arriving from the sun matched Bacal's prediction perfectly. They had just changed flavor en route. The key implication is this oscillation requires neutrinos to have distinct mass states. That means at least some neutrinos must have non-zero mass, something the original Standard Model did not include. This discovery forced a major revision in particle physics. But once we accept that neutrinos have mass and can oscillate, the next question is unavoidable. What happens when these messengers carry extreme energy and the Earth itself becomes part of the experiment? Let us return to the Mediterranean anomaly of 2023. The detection of an event with an estimated energy in the 200 PeV range is statistically jarring, but the silence accompanying it is even more profound. Why did IceCube, the titan of neutrino astronomy, located at the South Pole, with an instrumented volume 10 times larger than KM3NeT record, no comparable signal? To solve this, we must look at the geometry of the detection. We have to think in terms of ballistics. Neutrino detectors don't simply gaze upward like optical telescopes. For many analyses, they use the Earth itself as a filter. The planet acts as a shield against the constant bombardment of atmospheric muons, charged particles, produced by cosmic rays hitting the upper atmosphere. To see a clean signal, physicists typically look down through the bulk of the planet, using the entire Earth to filter out the noise. However, the event on February 13th arrived at a specific Earth-grazing angle. It did not come from straight down nor straight up. It skimmed the planet's crust. Based on the reconstruction of the muon track, the particle entered the KM3NeT detector after traversing a specific chord through the Earth's outer layers. Here lies the critical difference. Because KM3NeT is submerged 3.5 kilometers deep in water, and the event arrived at a very shallow angle close to the horizon, the particle had to travel through approximately 140 kilometers of rock and water, overburden, before triggering the sensors. Contrast this with IceCube. For a similar trajectory at the South Pole, buried only about 1.5 to 2.5 kilometers in the ice, the particle would traverse a significantly shorter column of matter, perhaps only 14 kilometers. This discrepancy in chord length, 140 kilometers versus 14 kilometers, is the smoking gun. It turns the entire scenario into a comparative materials test. The small bucket KM3NeT caught the rain not because it was bigger, but because it was positioned behind a thicker wall. This implies that the thickness of the wall matters. The mystery isn't just what was detected, it's why two giant instruments see the same sky so differently. The silence of IceCube suggests that 14 kilometers of matter was insufficient to generate the event, or insufficient to filter the background, while 140 kilometers was the Goldilocks thickness required to reveal the anomaly. At these extreme energy scales, the rules of engagement change. We are conditioned to think of the Earth as transparent to neutrinos matter they pass through, with almost no interaction. At low energies like those from the Sun, this is true. But at energies of hundreds of peta-electron volts, interaction probabilities rise enough that the Earth starts to matter. As the energy of a neutrino increases its cross-section, the probability of it colliding with an atomic nucleus rises dramatically. At the energy levels inferred from the KM3NeT event, the Earth is no longer transparent. It becomes opaque. A standard model neutrino with energy in the hundreds of PeV attempting to travel through the Earth's center would almost certainly be absorbed before it reached the other side. The planet acts as a literal beam stop. This effect is known as Earth opacity. If you look straight down for ultra-high energy neutrinos, you see a shadow because the Earth blocks them. If you look straight up, atmospheric muons become a dominant background. The only window of opportunity is the horizon, the grazing angles where the path through the Earth is thick enough to strip away the atmospheric noise, but thin enough to let the signal survive. The 140-kilometer chord length traversed by the KM3NeT particle sits in a unique ballistic window. It functions as a massive planetary-scale filter. It is a matter filter. The standard physics interpretation faces a dilemma here. A standard neutrino could survive 140 kilometers, but the probability of it interacting inside the detector volume after that journey, while IceCube with less shielding saw nothing, creates statistical tension. The 140 kilometer path acted as a natural filter and a target medium for rare interactions. It stripped away the noise, but it also seemingly interacted with something that required that specific density and distance to reveal itself. We are left with a physical tension in the interpretation. The event was too energetic to be a standard atmospheric neutrino, yet it appeared in a geometry that favors interaction. The planet has turned from background scenery into an active component of the detection system. The Earth filtered the beam, and something exotic survived the passage. If the standard messenger's normal neutrinos should have been either absorbed by the Earth or drowned out by noise in a thinner shield, then we are forced to ask what exactly made it through the filter. If standard neutrinos should have been significantly attenuated by the Earth at these energies or detected by IceCube's larger instrumented volume, we are forced to look at the lineup of remaining suspects. The list is short, and every option is uncomfortable for the current standard model. The most intriguing profile to emerge from the shadows is not a neutrino at all. It is a particle of dark matter. For decades, we have visualized dark matter as a cold, sluggish halo holding galaxies together, a gravitational glue that moves slowly and interacts with nothing. But that profile describes the bulk of the invisible universe. It does not account for the outliers. Just as protons can be accelerated to near light speeds by cosmic engines to become cosmic rays, theoretical models suggest that dark matter can be boosted. The engine for this acceleration is the blazar, a supermassive black hole at the center of a distant galaxy feeding on matter and spitting out relativistic jets of plasma. These are the supreme particle accelerators of the cosmos. In this high-energy environment, protons are whipped up to extreme velocities. When these high-speed protons collide with the ambient dark matter surrounding the black hole or in interstellar space, they can transfer their kinetic energy to the dark particles. The result is boosted dark matter. It arrives at Earth not as a slow-moving halo particle, but as a highly energetic, fast-moving candidate. This candidate fits the Earth-grazing profile perfectly. Unlike a standard neutrino, which might have a cross-section that makes the Earth too opaque at 200 PeV, a specific type of dark matter particle could possess the Goldilocks interaction rate. It would have a cross-section small enough to punch through 140 kilometers of rock without being absorbed, yet large enough to interact violently once it enters the detector volume. It survives the filter that stops the standard suspects. To test this hypothesis, we must look deeper into the collision point itself. We need to analyze the energy fingerprint left at the scene. At these energies, interactions are described in terms of deep inelastic scattering, where the incoming particle transfers energy to quarks inside a nucleon. Imagine the collision. The incoming particle does not bounce off the atom. It smashes into the nucleus, targeting a specific quark within a proton or neutron. This impact disrupts the structural integrity of the proton, shattering it. The kinetic energy of the incoming particle is then converted into two things: a hadronic shower, a cascade of subatomic debris, and a high-energy muon that streaks away, leaving the track we observe. This is where the forensics become granular. We look at the inelasticity parameter denoted as Y. This value tells us how much of the incoming energy is dumped into the shower versus how much is carried away by the muon. For a standard neutrino interaction at these energies, the physics is well constrained. In neutrino interactions, the energy is shared between a hadronic shower and an outgoing lepton. The exact split is described by the inelasticity parameter, Iy, and it varies event to event. It is a clean shot. However, theoretical models for boosted dark matter suggest a much harder collision. Some dark sector scenarios could shift the expected inelasticity distribution, leading to unusually large energy deposition compared with typical neutrino expectations. The event at KM3NeT was marked by an immense energy deposition. If further analysis reveals that the ratio of energy in the cascade was anomalously high compared to the muon track, it would be a strong clue. It would suggest a particle that interacts with matter more heavily than a neutrino. We are looking at a collision signature that defies the standard profile. One event cannot settle the interpretation. It could still be a statistical fluke, a rare neutrino, that managed to thread the needle. But the circumstantial evidence is mounting the silence of IceCube, the specific chord length of the Earth's crust, and the immense energy of the collision. The candidate list is short, and if a dark sector explanation holds up, it would reshape how we search for new particles. It means the invisible sector is not passive. It would mean the dark sector might leave detectable traces under very specific geometries, and we may only be sensitive to them when the Earth itself acts as the right kind of filter. We are standing on the threshold of a new observational era. The event of February 13, 2023, whether it proves to be a statistical anomaly or an early hint of dark sector physics, has served a critical purpose. It has exposed the limitations of our current vision. A single flash in the Mediterranean has shown us that the Earth is not just a rock we live on, but a scientific instrument, a natural filter we can exploit by observing through different chord lengths of Earth. But to truly map the invisible 95% of the universe, we need eyes that are grander in scale. The next generation of hunters is already rising. In Antarctica, the IceCube Gen 2 project plans to expand the optical array to 10 cubic kilometers of ice, increasing the detection volume by an order of magnitude. In the Pacific, the P1 Observatory is preparing to turn the ocean floor into a sensor array. In the South China Sea, the Trident project aims to build a massive, attentive eye to catch these transient, high-energy messengers. We are moving toward a planetary-scale network with detectors across ice and ocean working in concert. This ambition is driven by the ultimate prize, the cosmic neutrino background, or CNB. These are relic neutrinos from the early universe formed in the first seconds after the Big Bang and still filling space today. They are everywhere, billions passing through us every second, but they are so low in energy that detecting them remains beyond today's technology. The desperation to catch them has even led theoretical physicists to propose radical thought experiments, such as the detector accelerator. The idea is to take a massive detector and accelerate a detector to extreme speeds so that background neutrinos would appear higher energy in its frame. While currently science fiction, it illustrates the lengths to which human curiosity is willing to go. So we return to the question that began this investigation. Is the 200 PeV event a message or a warning? If it is a message, it tells us that the universe is far more violent and energetic than we dared to model. If it is a warning, it signals that our standard model is incomplete, that there are forces and particles in the dark sector capable of piercing our planetary shields in ways we did not predict. The silence of the abyss has been broken. The universe is screaming at us in a language of invisible particles and high-energy collisions. For a century, we were deaf to it. But now, deep under the ice and beneath the waves, we are finally learning how to listen. The question remains open, and the next decade of data will decide what this signal really was.